This is part 3 of section 9.4, which is partial fraction decomposition. So again, each one of these examples that I'm giving you has different things that show up in other problems. They might have one thing from example number 1, and it might have something from example number 2, or something from example number 3, all in one problem. And so you need to know how to handle that. But I've come up with these 3 different examples to try to cover all the different things that you are possibly going to have. Now this one is basically where, let's say that your denominator started off looking like this, x cubed plus x, and we want to break it apart into some fractions. Well, your first step is always going to be to factor the denominator. So I already have this in factored form. The problem is that, yes, it factors, you can factor out an x, but then this part, x squared plus 1, is not factorable. It's not the same as having just x squared. X squared technically would be x being repeated as a factor, but this is x squared plus 1. That if it was x squared minus 1, like this, if it was x squared minus 1, I'd be able to factor that into x minus 1, x plus 1. I'd be able to break it down into linear factors. But that's not what I have here. I don't have x squared minus 1, I have x squared plus 1. And so it is something that cannot be factored anymore. And it is called a quadratic factor because it has x squared as part of a polynomial and it's not factorable. So this factor is just x to the first power. So it is linear. This one has x squared as part of a polynomial, so it's quadratic. And they're definitely different from each other. So distinct just means that they're different from each other. So we need to know how to handle that situation. So it is different because of the quadratic factor there. So I still have 2 factors in my denominator, so I'm still going to break it down into 2 fractions, where my first fraction is going to have that x, and my second fraction is going to have this factor, which is x squared plus 1. So the first part, setting it up, is going to be done the same way. If it's a linear factor like this, just like before, I'm just going to put a letter over it. I want to figure out what that numerator is. The problem is, this one is quadratic, so this is where it differs a little bit. In order for this to still be a fraction that's not improper, I can have an x on top, because x to the first power, if I had an x to the first power over x squared, that's not an improper fraction. So it's possible that this might have an x in the numerator, where this one, because the denominator is linear, you're not going to have a variable up on top, because then that would be an improper fraction and you'd be able to reduce it. So this one might have a factor with an x in it on top. So if it did, it would have a coefficient in front of it, and then it still could have a constant at the end. So every time you have a quadratic factor, it's going to have a numerator that's going to be something x plus something. And since I already used a here, a is already being used here, then the next one is b, and the next one is c. If I had another factor, it would go to d, and if it was quadratic, it'd be dx plus e, and so forth, okay? So that's just the way that we go about setting up the numerator. So again, linear denominator, you only put a letter on top. Quadratic factor, so something with an x squared that cannot be factored, so it has to be part of a binomial. You put a binomial on top, and you put a letter in front of the x and a constant after it. So it's all in the setup. So once you have the problem set up, it is pretty much like every other problem that I've done so far. So once I have this set up, I want to get rid of these denominators. So this denominator is the key. This denominator has an x and an x squared plus 1. So I'm going to multiply by that. And so I'm going to multiply this times x squared plus 1. And I multiply this one by x times x squared plus 1. And by doing that, I can eliminate my denominators. This x in this denominator cancels out with that x. This x squared plus 1 cancels out with that x squared plus 1. That's why I multiplied by it. I've gotten rid of everything on the left side except for the x squared minus 1 that's over here. On this side, this x in the denominator will cancel with that x. So I'm left with a times x squared plus 1. Likewise, in this one, I have an x squared plus 1, I can cancel that out, so I'm left with x times bx plus c. Now this is where things are going to get a little bit different. When you start having quadratic factors, you're going to want to do it using the method I'm about ready to show you. And so if I were to simplify that, bx times that x, I'm going to distribute it, become bx squared and then plus cx. So if I start simplifying the right side as much as I possibly can, I would distribute this a, I'd get ax squared plus a plus bx squared plus cx. So notice how that's got an x squared and that has an x squared. So I would like to put those together. Just like if you had like 5x squared plus 7x squared, you would add together the 5 and the 7 to get that to be 12x squared. But instead of 5 and 7, I have a and b, but I still do it the same way. I'm going to add together the a and the b x squared. So I've combined those together. So that's x squared. The next one I want to put down is my linear term, so plus cx. And then the constant, this doesn't have a variable with it, and so I know it's a, but it doesn't have an x with it, so that's going to go last. Okay? So this is where the technique differs. On the left side, I have x squared minus x. So notice, let me back that up for a second. I have x squared, and I have minus 1, but there's no x term. Like this has an x squared, this has an x, and this has a constant at the end. This has an x squared. There is no x term there, right? So I'm going to fill that in though, because this is a 1x squared plus 0x minus 1. The reason I'm setting it up like this is that if you have a quadratic on one side of your equation and a quadratic on the other, which I do have here, you can actually take things that correspond for coefficients and set them equal to each other. So for example here, 1x squared. The coefficient of x squared here is a 1. The coefficient of x squared on this side is a plus b. Because this is an equation, for this to be equal, those have to be equal. So I'm able to say 1 equals a plus b. Now, likewise, that x has a 0 in front. There's a reason I did that. It has a 0 in front. That means this x has a c in front. Those have to be equal to each other. So c is equal to 0. And then lastly, I have this minus 1 is my constant at the end. This is my constant at the end. So a and negative 1 correspond with each other. So a is negative 1. So now that I know c is 0, I know a is negative 1, I can use this as a system and figure out what b is. Because a is negative 1. If I add 1 to both sides, I would get b is equal to 2. So going back to my original problem, this is what I originally broke it down into. What I was looking for was what's a, what's b, and what's c. I now have that figured out. So that means that now I could write my answer. My answer, I would just simply rewrite this, but replace the a, b, and c with the values that I found. Notice, it is perfectly fine for either b or c to come out to be 0. It's just whatever is needed for it to create that equation. Okay? So this is just the same process I just did, except I had it typed out. So this side was x squared minus 1. This is after I multiplied both sides to get rid of the denominators. Started organizing things. Same thing I had here. We were able to say that a plus b is equal to 1. We were able to say that c was equal to 0 and a was equal to negative 1. And then that allowed me to figure out that b was 2. So then this is what I was saying, that here's what I originally had, equals, I found out that a was negative 1, so I rewrote that. B was 2 and c was 0, so I'm able to leave that off.